Hello everyone, in today's lesson we're going to discuss key features of polynomial functions, some examples, how the graph looks like, how to analyze the graph, how to get end behavior, and other interesting facts about the polynomial. But first, let's begin by actually describing what is the polynomial function. So using the function notation, we're going to name it with either f of x, g of x, h of x. So we're going to use different letters, and we're going to use function notation for that. As you can see, this is a general form of a polynomial function. It starts with adding each term. So an represents any real number, and exponents represent the degree of the polynomial. So this is a general form because we don't know what the coefficients are. The first coefficient, so an right here, it's going to be a constant, a real number, and I'm going to call it a leading coefficient. So this is a leading coefficient, and the leading coefficient is going to be very important for us. So here are some examples of polynomial functions, and we're going to classify them by degree. Remember, degree is just the highest exponent in the polynomial, so we're going to look at that and going to get the leading coefficient. Leading coefficient is a constant. It's actually a coefficient of the term with the highest degree, with the highest exponent. So if we look at the first function, f of x equals 4, it has no variable. So it's a constant function, and constant functions have degree 0. And the leading coefficient is 4 in this function. Then the second example, f of x is equal to negative 5x plus 1 is a linear function, and the degree is going to be 1 because there's a variable x and it has exponent 1s to the first power. So degree is 1, and the leading coefficient is negative 5, is the coefficient actually of the first term. The third example, f of x 12x squared minus 11x plus 31, the highest exponent is 2, so there's a degree 2, and the leading coefficient is 12. Alright, go ahead, pause the video, and try to figure out the remaining 3 examples. Alright, let's go over. So the degree of the next example is 3. The leading coefficient is negative 1. Then we have degree 4, leading coefficient negative 3. Degree 5, leading coefficient 9. Alright, let's talk about parent functions. And we need to recognize what the parent functions are. There's a constant function that it's going to be written as f of x is equal to a constant, some value. I'm just going to use letter c for it because that's going to change, like 2, 0, negative 5, and so on. So a constant function is going to be a horizontal line passing through c. Linear function is going to be in the form f of x is equal to x. So this is a parent function. It's just the basic linear function that goes through origin, and the slope is 1 over 1. So this is a parent function of the linear function. Quadratic function is going to be f of x is equal to x squared. And this is a quadratic function, parabola, that its vertex is at the origin, and this is just a parent function. Cubic is the third degree polynomials, so it's x cubed, and x cubed, all of them are actually going to pass through origin, and x cubed is this function going up and down. Later on, we're going to discuss end behavior as x approaches infinity. So this is x approaching infinity or negative infinity. What happens to the graph? What happens to the value of the function? So we're going to look at the ends, where the arrows are pointing. So if you can look at the linear function, the right side of the linear function is actually approaching positive infinity, so it's going up, and on the other end is approaching negative infinity because it's going down. If you look at the quadratic function, both ends are pointing up, so the end behavior is positive infinity on both ends because it's going up. When you look at the cubic function, one end is going to positive infinity and the other end is approaching negative infinity. Okay, we have two more. Quartic is the function that is going to look very actually similar to the quadratic function, but it's going to be a little flatter at the bottom. So it's going to be a little more square. And this is f of x, it doesn't want to write, is equal to x to the power of 4. Alright, okay, I got it. Alright, and again, the end behavior, both ends are pointing up. So the end behavior is both positive infinity. Quintic is f of x is equal to x to the power of 5. And it's going to look very similar to x cubed, but we're going to get it more flat around the origin. And the end behavior, one end is going to negative infinity, the other one's going to the positive infinity. So it's going down and up. So we're looking at ends. That's what the end behavior is, and that's where we actually, it brings us to the next section, to examples 1 through 6. And I would like you to use Desmos if you don't have a graphing calculator at home. So use desmos.com to graph examples 1 through 6 and look at the ends, look at the graph and write what happens on the right side and on the left side. And then pause the video. When you're done, unpause and check with my answers. Alright, so let's go over. Example number 1, 4x to the 4th plus 6x cubed minus x is the 4th-degree polynomial, so it's a quartic polynomial, and you can kind of like compare it to the one a little bit above, right here. So we know that when x gets really, really large, the y value are going to be approaching positive infinity. And same thing will happen when x gets really, really small, approaching negative infinity. The y value, so the value of the function is going to approach positive infinity. So they're both up and up. That's what we commonly say. All right, example number 2 is a quadratic function, but when you graph it, it's going to face down. So both ends are going to approach negative infinity. I hope you had a chance to actually look at the graph. 2x cubed is a cubic function. It's going to be an increasing function. So one end is going to approach positive infinity and the other one's going to be approaching negative infinity. So it's down and up. Negative x cubed, the graph is going to flip. So now the left side is going to go to negative infinity and positive infinity. Example number 5, it's a quadratic function facing down, so both ends are going to be going towards negative infinity. And number 6 is a cubic function, actually increasing from left to right, so we're going to have positive and negative infinity. Alright, how to remember it? So this is going to be kind of like a cheat sheet for you. This table is going to help you remember how to recognize end behavior. And the sketches are going to actually help you do that. So when we have a positive leading coefficient, so this first constant is positive, and you have an even degree, both ends are going to go up. If we have a negative leading coefficient, then we're just going to flip the graph. If it's odd degree and a positive, it's going to increase from left to right. And if the leading coefficient is negative, first it's going to go up and then go down. and the arrows are going to help you determine the end behavior. So let's look at the graph and let's try to figure out what's going to be the leading coefficient. And we're interested not at the value, but actually of the sign of the leading coefficient. So since we know that the end, let's start with the end behavior. End behavior, both ends are actually going down and down. So by looking at the table right above, we know it's going to have an even degree, because this is where we're going to actually look, right there. That's number 7. So which means we're going to have an even degree and a negative leading coefficient. So leading coefficient is going to be negative, not -1, just negative. And we're going to have even degree. In number 8, we have down and up. So now let's look at the table, and this is the actual pattern that we see right here, which means we're going to have odd degree and a positive leading coefficient. So the leading coefficient is positive and degree is odd. So that's how we recognize patterns on the graph. All right, we have, of course, more features on the graph, and we can get more information from a graph than just end behavior and leading coefficient. We're going to look at the turning points, and the turning points are the points at which a polynomial function switches direction. And if the turning point is higher than any nearby point, we call this point a relative maximum. And the relative maximum is going to be a point that's higher than all the points around. So this is a relative max. And then if the turning point is lower than any nearby point, it's called a relative minimum. So here, this point up here is a relative min. Maximum and minimum values are called extrema. So that's a new word. Extrema. So extrema refer to either maximum or minimum. And turning points define where the function is increasing or decreasing. So now we're going to actually we're going to be using graphing calculator or desmos.com if you don't have a graphing calculator, and we're going to graph and get some features. So to graph a function, you're going to enter the function in y equals, and then you're going to hit graph to see how the graph is looking and behaving. Step number 2, you're going to use the Calc menu to find the minimum and maximum values. And you're going to move the cursor to the left bound of the turning point, hit enter, then move the cursor to the right bound of the turning point, and then you're going to hit enter twice. And then it's going to ask you for the minimum or the maximum. So this is the function I want you to graph. So f of x is equal to x cubed minus 6x squared plus 7x plus 2. So take a moment, open up Desmos or get your graphing calculator ready, graph it, follow step 1 through 3, pause the video, and then we're going to talk about it. So roughly sketching this graph, I'm just going to switch my pen. Okay, the graph roughly looks like this. more or less. Of course, the graphing calculator it's a little bit, but this is a general idea. So what we have, so the relative maximum is going to be right here. So this is your max. Here's your min. And then increasing interval. So we go, this part of the graph is increasing, and this part of the graph is increasing. So we have two intervals of increasing, and then there is one part where the graph is going down. So this is the decreasing interval. And the intervals go from, we're going to use the x values to determine them. So we go from, these are the crucial points actually on the graph. So the relative maximum, if you use your calculator, this point, it's a point. So we're going to, it's about 0.7 and 4.3. The relative minimum, it's 3.29 or 3.3 and negative 4.3. So the increasing intervals, we have two. And the first one starts at negative infinity and it goes all the way to this point right here, to the maximum point. And that maximum point happened to be at 0.7. So that's one interval. And the second interval is actually starts at the minimum and goes to positive infinity. And the minimum happened to be at 3.29 to positive infinity. There's only one interval of decreasing, and that's going to be the one in brown on my graph, and that's going to be between your maximum, which is 0.7, and your minimum, which is 3.29. Alright, and the last one, I know this lecture is a little longer than other ones, and the last one, let's put it all together and let's graph the polynomial, and then let's find its domain, range, relative maximum and minimum if it exists. Sometimes there's more than one. Then we're going to look at the end behavior, intervals of increasing and decreasing. So first let's start, open up your Desmos or have your graphing calculator, and let's graph negative x cubed plus 3x squared. Alright, so let's create some table of values so we have some few x values to graph, so our graph looks, it's not a sketch, it's actually a graphed function. So negative 1, 4, you can access your table pressing second and graph. Then we have 0, 0, 1 and 2, 2, 4, 3, 0, and then we have 4 and negative 16. I don't think we can fit negative 16 on our graph, so we're going to plot only points that are feasible to graph on the graph. So negative 1 and 4, the point is right there, 0, 0, so it goes to origin. Okay, 1, 2, 2, 4, 3, 0, and 4 negative 16. I don't think we can fit that. Let me fix this point to origin. And by looking at your calculator or your Desmos, just make the best effort and just connect them with a smooth curve. So this graph looks a little bit like that. So we're going to look at the domain. Domain are all, you're looking at the x value, so you're looking horizontally. And if you can see, there are no breaks in between, so the domain R is actually all real numbers. So we go from negative infinity to positive infinity. So we're using interval notation. The range. So the range we're going to be looking at vertically all the y values. Where does the graph begin and where does it end? Do we have any breaks in between? If we can see, the graph is continuous and it goes from negative infinity to positive infinity, which means that both domain and range are all real numbers. Now let's find the relative maximum. So the relative maximum is going to be right here, this point right there. So this is your maximum. It's called relative because it's not absolute. So relative maximum happened to be, I think, the highest point when you look at the table. It's going to be, I believe, it's the point that corresponds to 4. And the relative minimum, it's right here. So this is your min. And minimum is just origin 0, 0. What happens with the end behavior? When x gets really, really large, so you look to the right of the graph, the actual, what happens to your y values? Where does the graph go? Let me just switch my colors. So here it goes towards negative infinity. So the right side goes towards negative infinity. And when the x's are getting really, really small, the graph goes to positive infinity. That's your end behavior. Increasing interval. So this is where the graph is actually increasing, going up. And the graph is going up only right here. This is where it's going up. So it goes from min to max. And my min and max are going to be from 0 to 2. We're using x values to denote the intervals. And decreasing intervals. Decreasing intervals are here and there, where the function is going down. So the first green arrow goes from negative infinity to 0. And the second part starts exactly at the max, so at 2 and positive infinity.